Hey everybody! Today we're going to pick up where we left off last time with our compound interest formula, and we're going to see what happens if we can go into continuous compound interest. Now, if we remember from last time, we said that compound interest means after a certain amount of time after you've borrowed money from me, I'm going to take the amount of interest earned, roll it back into the principal, and then that principal plus interest is going to start earning interest. So I'm essentially increasing the amount of money that's accumulated that I get when you ultimately pay me back. And we found this formula right here. And we said that A is the amount of money accrued, P is the initial amount borrowed, or the principal, R is the interest rate per unit time, N is the number of compounding periods in 1 unit of time, and T is the number of units of time. And we said that as a human civilization, we've decided that T would be represented in years. We care about time in calendar years. So that means N is the number of compounding periods in 1 year, and R is the interest rate per year, or the percent per year. And then we calculated some values for different values of n given t 1 through 5. And we showed that for any time period t, that as we increased n and we went horizontally this way, we saw that it was always getting bigger. So as I increased my compounding periods per year, I would always be accruing more money. And then we tried the crazy thought experiment and we said, what if I compounded so many times in 1 year, I might as well be compounding infinitely many times per year. So ideally that means in the most infinitesimally small period of time, however much interest is accrued, it's instantaneously rolled back into the principal and I'm earning interest on that interest at every infinitesimal moment of time. In other words, I'm continuously compounding my interest. And we said, what would that look like? And that we'd be saving it for next time. And next time is here, so here we go. Okay, now before we actually get into exploring continuous compound interest, we're going to take a minor detour and we're going to examine this expression right here, which may seem completely unrelated, but it's going to turn out we're going to need it later. So what we have right here is 1 plus c all raised to the power of k. And we're going to set some limits on these two variables we have showing here. First, we're going to say we want what's in this parentheses to be positive, which means we want it to be greater than 0. And so we say, okay, well, what does c have to be in order for that to be true? Well, let's just set it up that way. I want this to be true. I want 1 plus c to be greater than 0. So I just solve for c. Well, that means I subtract 1 from both sides, and I get c is greater than negative 1. So that's my first restriction that I place on this. I want c to be greater than negative 1. And then next I say I want k to be a natural number. And if you remember from before, natural numbers are just our counting numbers. 1, 2, 3, and so on into infinity. So k is a natural number, c is any number, but it has to be greater than negative 1, and thus what's internal to my parentheses is always going to be positive. Now what we're going to do is we're going to explore some things by plugging in different values for k and seeing what we get. So let's just start with the first value for k. So let's just let k equal 1, and then let's see what we get. Well, I have 1 plus c to the power of 1. Well, anything to the power of 1 doesn't change, so I just stay the same. I'm at 1 plus c. And I'm not gonna lie, that's pretty boring. I may not care about k equals 1, but for now I've at least explored it. All right, let's keep going. Let's let k equal 2. So I substitute that in, 1 plus c squared. And hopefully you remember how we can actually expand this expression out. We did this when we did the Pythagorean theorem. When you have the exponent of 2, you're just multiplying by itself. So this is 1 plus c times 1 plus c. And then we distribute, where I take each term from the first one and multiply it by each term from the second one. So I can take the first and the first, 1 times 1, and that's 1, plus the first and the last, it's 1 times c, plus c, plus the second and the first, c times 1, that's c, plus the second and the last, c times c, that's c squared. And now we simplify by collecting like terms. I have 1c here and 1c here. I'm going to bring this over here. And so I have 1 plus 2c plus c squared. I combine these two things together. And now what I'm going to do is I'm going to set this aside in my mind, and I want to know what's being done to this portion. What's being done to 1 plus 2c? Well, I'm adding c squared. And we can say something about c squared for sure, because we know that c has to be greater than -1, which means it could be negative or it could be positive. But square any negative or any positive number and you always get a positive number. Positive times a positive, always positive, but so is negative times a negative. In other words, no matter the value of c, c squared must be a positive value, which means I'm adding something to 1 plus 2c that will make it bigger, which means I can say this must be true. This must be greater than 1 plus 2c. So what I started with was 1 plus c to the power of 2, and I've shown that it must be greater than 1 plus 2c. Okay, does that mean anything? Well, let's explore one more. Okay, now I'm going to let k equal 3 and see what happens. So here I have 1 plus c cubed to the power of 3, and if I were to expand that out, well, I would write that as 1 plus c times 1 plus c times 1 plus c. Now that may seem like a lot of work, but we've already done a good chunk of it up to this point. We've already done 1 plus c times 1 plus c. That's what we just did when we set k equal to 2. So I can substitute in that result right here and then multiply that by 1 plus c. And so that's what I'll do next. This gives me 1 plus 2c plus c squared, which is what we just found when k equaled 2. That is being multiplied by 1 plus c. Now, in this case, I'm not multiplying something with 2 terms times something with 2 terms. It's 3 terms times 2 terms, but the principle's still the same in terms of distribution. I'm still taking every term from one multiplied by every term in the other. So let's do that term by term. I've got 1 times 1, and that's 1. And then I've got 1 times c plus c. And then I've got 2c times 1 plus 2c. And then 2c times c plus 2c squared, and then c squared times 1 plus c squared, and then c squared times 3. I'm sorry, c squared times c is c cubed. So this is these three things, or this thing cubed, expanded out. Now I simplify, look for like terms. The first set of like terms I see, I have 1c here and 2c's here. So as I simplify this, I'm going to write this as 1 plus 3c plus, now I see here I have 2c squareds and 1c squared. So I have a total of 3c squareds. And then finally I've got c cubed on the end. So this is the simplified version of 1 plus c cubed expanded out. And again, in my mind, I'm separating out these first two terms, 1 plus 3c, and I'm looking at these last two terms being added to it to see how do they affect this part's value. Well, just like last time, taking a look at this first term here, I have a c squared, which means that has to be positive no matter the value of c, times a positive 3. So again, I'm staying positive, which means this term must be increasing 1 plus 3c. But now I've got something a little more difficult. I've got plus c cubed. Now, if c is positive, well then I've got positive times positive times positive, and it's positive. Therefore, this is also adding to this value, making it bigger, and we know that these are both making this bigger. But if c is negative, negative times a negative is negative, which means I'm actually subtracting a value from here, and thus lowering what I've done here with the plus 3c squared. So now we need to look and see how much am I lowering it here compared to how much I'd be adding it here. Well, when we look at it this way, what we're going to actually focus on is the magnitude of c, or the size of c, which basically means I ignore the sign and just look at the size of the number. It's something we call the absolute value. And we write that out with two vertical bars. So I'm concerned now only with the absolute value of c, the magnitude or the size of c. And we recognize from up here that if c is negative, it has to be between -1 and 0. I've put that restriction on it. So its size is between 0 and 1. So in other words, it's actually smaller than 1. Its absolute value is. Now, if you multiply by a number that's smaller than 1, you get smaller. And you can kind of think about that from patterns. If I multiply by a number bigger than 1, I get bigger. If I multiply by 1, I stay the same. So if I multiply by a number smaller than 1, I get smaller. So let's kind of build these two terms piece by piece to see how their sizes compare to each other. So again, focusing only on the absolute value of c, I think I start by building both of these terms with a c. Okay, so they're the same. And then I'm saying, okay, I'm multiplying by 2 c's here and at least 2 c's here. So I can go ahead and put like a squared on both of those. I'm still building them up, so they're still the same. And then on the left side, I'm multiplying by 3. Well, now remember, c is less than 1, and I've taken this number and multiplied by a number bigger than 1. So this gets bigger. This increases from where I just was. And then over here, I'm multiplying by c again. And so I was at c squared. When these were both at c squared, they were equal in magnitude. But now when I multiply by c again, we said c is less than 1. That means it must shrink from where I was, from c squared. So again, now knowing that their magnitudes, this is a bigger magnitude and this is a smaller magnitude, I know this is positive. We said so before, and if c is negative, then in this case, then this would be negative. So I'm subtracting it, but I'm subtracting a value that's smaller than what I'm adding to it. And that's a long way to go to finally say it must be true then that this whole expression is just greater than 1 plus 3c. Meaning that 1 plus c cubed is greater than 1 plus 3c. Now that took a long time. I'd really rather not explore any more, like starting with k equals 4 on up. So we're going to take a page out of our book from the compound interest video where we use something called induction, and we're going to see if that will work for this too. Okay, remember for induction, we start with a claim. I have an idea that I hope is true. My claim is that if I take 1 plus c to the k, that it must be greater than 1 plus kc for c greater than -1 and k greater than or equal to 2. That's my claim. Now, to see if I can prove that, we have to do this in 2 parts. First, we say find a value for which it's true, specifically the lowest value. So in this case, we look at k and we want to set it equal to 2. And I want to demonstrate if that's true or not. Well, that's actually what we just got done doing. I already showed that it is in fact true. So I can write this down and say that 1 plus c to the 2 is greater than 1 plus 2c. So that part is done. We've already done that in our exploration. Part 2 says, all right, assume it's true for some value of k. Let's call that value j. So by assumption, I let this be true. When k equals j, then 1 plus c to the j must be greater than 1 plus jc. That's true by assumption. And then I say, what happens if I increase k by 1? So now I let k equal j plus 1, and we see what happens. Now for this part, I'm actually going to start with what I've already assumed to be true. I'm going to start with that statement, 1 plus c to the j is greater than 1 plus jc, and I'm going to multiply both sides by the same value, so the expression stays the same. So I'm going to multiply both sides by 1 plus c. So this would give me 1 plus c times 1 plus c to the j is greater than 1 plus c times 1 plus jc. Now we can do that because we said 1 plus c must be positive. By making c greater than -1, 1 plus c must be positive, and when you multiply both sides of an inequality by a positive value, the inequality stays the same. I'm hoping you remember from algebra that if you multiply by a negative value, the inequality flips. And that's basically the reason why we don't want a negative value inside here, because we don't want to flip that. We want it to be positive. All right, now I just kind of combine and expand and see what happens here. So on the left-hand side, I'm just multiplying by one more 1 plus c. So this 1 plus c to the j is really no different than 1 plus c to the j plus 1, which is ultimately what I'd want on the left side based on my claim. And then I have is greater than. Now I'm going to expand the right side the same way we've been doing it. So I take 1 times 1, and that's 1, plus 1 times jc, and that's jc, plus c times 1, and that's c, plus c times jc, and that's jc squared. And then I simplify, look for like terms. I've got jc's here and one more c here, so I can combine those and say this is really 1 plus j plus 1 c's plus jc squared. And again, in my mind, I'm separating out this first part, this 1 plus j plus 1c. I'm choosing that again from my claim, because that's what I'd want based on k equals j plus 1, and I'm exploring what does this last term do to this value. Well, I've got a j and a c squared, and again, c squared must be positive, and j must be positive. Well, why must j be positive? Because j is a value that we know makes this true, and it substitutes in for k, and we said k has to be greater than or equal to 2. Well, that means it has to be positive, so does j. So I'm taking a positive times a positive, which means I'm adding a positive value to this part of the expression, which means I'm making it bigger, and so I can say then that it must be greater than 1 plus j plus 1c. But that's exactly what we wanted to show. We said if k equals j plus 1, I want to put that into my claim. I've got 1 plus c to the k, which is j plus 1, has to be greater than 1 plus kc, where k is j plus 1c. And therefore I've shown it to be true, assuming, so I put a check there, I've done that part, assuming that it's true for some j. So if it's true for some j, it must also be true for some j plus 1. But I have found a j, haven't I? When k equals 2 or j equals 2, I know it's true. And so it must be true for the next one, k equals 3. Oh, well then it's also true for the next one, k equals 4, and k equals 5, and k equals 6, and so on into infinity for every natural number from there on. And therefore, I've proven my claim true by showing that it is in fact true for all k greater than or equal to 2. Now, I know this may seem abstract and weird. Where did this come from? Table it, and we're going to come back to it in a bit. Okay, back to our compound interest formula and the topic of this video, continuous compound interest. So we have to ask ourselves, what does it mean mathematically to think about something being continuous? And we said what we're really looking at is taking the value of n and increasing it basically to infinity. The challenge we run into is that infinity is not a number. I can't substitute in infinity in for n and then do some math and see what happens. Infinity is more like a destination, or maybe even more better, a direction. I'm headed in that direction. I can never actually reach it, but I'm never going to stop trying. And so to explore stuff that you can't reach, but that you can continuously head towards, we actually have to use calculus. Now, don't get scared. This isn't going to be a major mathematical calculus video here. In fact, we're only going to use really what's pre-calculus, the idea of something that's called a limit. This forms the basis and foundation for calculus, and I'll probably do some future videos on that. But for right now, it's more conceptual than anything else. So you're not going to be learning a lot of new math. You're going to be just learning a new way to apply your thinking to this math. So, what is a limit? Let's start with notation. We just use the first 3 letters, LIM for limit, and then we have to pick a variable that we're going to send into infinity. Well, in this case, it's n. So underneath, I write n, and then I use an arrow to denote the direction that I'm headed, and I said I'm heading towards infinity. And if you don't remember, infinity is just like a sideways 8. So this is the limit as n goes to infinity, and then I write my function. And my function is p times 1 plus r over n to the power of nt. Now that's nice, but it's kind of ugly. I care about what happens as n approaches infinity, but in the meantime, I got a whole bunch of things, p, r, and t, that are in my way. Now granted, they're constants, we know their values, but at the same time, they're still going to hinder me from really being able to explore this limit. So instead, we do a thought exercise, and we think about what are the possible outcomes of a limit as n goes to infinity. So what I want you to picture now is picture a graph. And horizontally is my n values. So as n goes to infinity, I'm going as far as I can to the right. And then vertically is my function value, or my compound interest formula, a. What happens vertically as n goes horizontally as far as possible? Well, we can experiment, or we can think about what are the possible things that can happen. So first, the limit could oscillate forever. So as I go to the right, I'm constantly going up and down and up and down and up and down, never narrowing in on a single value. Well, that basically means that the limit does not exist. And that's what we write. We say the limit does not exist. Okay? Next, as n goes to infinity, my function could increase forever. It could always be going up, never ever ever slowing down, never ever ever stopping at anything, always increasing. Well, at that point we say the limit exists, but that the limit equals infinity. And likewise, I could be always decreasing, which means my limit equals negative infinity. And then finally, we could say that the limit may be increasing, or the function may be increasing, excuse me, but that it's always getting closer and closer and closer to some specific value. Let's say it's 2. So I'm getting as close to 2 as I want as I go and go and grow, but never quite reaching it, but I can get as close as I want. Or, likewise, I could be decreasing towards a number, let's just keep it at 2, but I'm getting as close as I want but never quite reaching it. Okay, then we say not only does a limit exist, but the limit has a value, and that value would be 2. And along that same vein, I could be oscillating. I could be oscillating, but my oscillations are getting smaller and smaller and smaller as I go to the right, and maybe they're narrowing in on a specific value, and maybe that value is also 2. I'm just picking an easy number. But at that point, then we say that limit does exist, and we say that its value is 2. So when I think about that, I look at this and say, okay, I'm concerned with when n goes to infinity, so that's really this portion right here, and then I'm multiplying by p. How would multiplying the outcome of a limit change the outcome? Well, think about the first one. The limit doesn't exist. If I multiply by p, all I'm doing is taking my oscillations and increasing them, and just oscillating up here, still never reaching anything, and therefore the limit still doesn't exist. And if I grow without bound, and I grow towards infinity, and then I multiply by p, I'm still going to grow towards infinity. I'm just going to get there faster. And so it still grows to infinity. And likewise, if I decrease to negative infinity, if I multiply by p, I'm still going to decrease to negative infinity just a little bit slower, because p is a positive value. So it'll take me longer to get there, but I'm still going to get there. And finally, if I'm increasing toward a specific value, like let's say 2, or I'm approaching it from a decrease, or I'm approaching it from an oscillation, but either way I'm approaching a specific value like 2, and I multiply by a number, let's call it 3, all I'm really doing is just moving that up to 6, and now my limit is approaching 6. In other words, multiplying by a value does not affect the possible outcome of the limit. It only affects the value of the limit if the limit has a finite value. So I can actually take this p and move it outside. So that's what I do to kind of clean this up a little bit. So this is p times the limit as n approaches infinity of 1 plus r over n to the power of nt. So I've gotten rid of one variable from my limit. Next, I see t is on the outside of my limit. And it's being multiplied by another value in that exponent. And if we remember from our properties of exponents, then we know that I can really say this, it's like this t is sitting outside a set of its own parentheses. So I could insert these grouping symbols here, and to make it more clear, we'll usually use like brackets when we already have parentheses. And I say that's the exact same thing mathematically. And so now I say, well, wait a second. With this t out here, what am I doing to what's in here with my limit? Well, again, think about the possible outcomes of the limit, and then just raise it to an exponent. And that exponent is just repeated multiplication. So it's really the same thing we did when we talked about just multiplying by p. That t has nothing to do with anything in terms of the possible outcome. All it does is change the finite value if the finite value exists. And so, again, I don't need this t inside the limit. I'd actually rather have it outside the limit because it won't change the value. So I'm actually going to do that here by moving my bracket over to here. And as we can see, I'm starting to get it more segregated. Okay? What's inside these brackets is my limit. My limit that I'm concerned with, my variable, is n as it approaches infinity. and I've got n and n, but I still got that nasty, ugly r in there. And here's the problem we run into with this one. This r is not multiplying by the entire limit. It's not adding to the entire limit, and it's not being an exponent to the entire limit. Therefore, I can't just separate it out. So I have to use another trick from calculus. But again, this one's going to be really easy. It's just called a change of variables. And so what I do is I say, all right, I'm going to create a variable. I'm going to call it h, and I'm going to define it to be something that's going to be useful to me, and I'm going to call it n over r. So I say that h equals n over r. Now I'm going to solve for n, which means I multiply both sides by r, and then I'm going to just switch the sides of the equation just to make it easier, and I get that n equals hr. And now I'm going to substitute this in for my n's in my limit. Right? And now I'm going to leave out the p and the t just to make things a little bit easier for me. They're still there, but I'm only focused on the limit right now. And so I've got 1 plus r over, now for n, I write in hr, and for n, I put in hr. So now I've changed my limit a bit, and there's one other thing that I haven't done. I didn't carry down my variable down here. You may be thinking, well, substitute in hr for n. But now I would have two variables. And I don't want two variables as my limit variable, so I have to use a little bit of thinking power. And I come back up to here, and we know what's happening based on our limit, that n is approaching infinity. So if the left side of this equation is approaching infinity, then so must the right side. The right side must also be approaching infinity. In other words, growing without bound. Well, r is a constant. It's a percent per time, or per year specifically. It doesn't change. It's a known value that just sits still. So as a graph, it's a horizontal line. That does not grow without bound. It stays put. So that r does not contribute to the growth without bound, which means h has to contribute to that. Well, if h is constant, then it's just a horizontal line. And r, we know, is a horizontal line. Then hr is just the product of these two, and so it's just a horizontal line. It does not grow without bound. Well, that's not possible because we know hr must grow without bound because n grows without bound. So therefore, h can't be a constant, and h has to grow without bound. So the portion of hr that actually grows without bound is purely based on h. It has nothing to do with r. So as I look at my limit, I can say, I don't care about substituting in hr for n. I actually only need to substitute in h, because I only care what happens as h approaches infinity. And so that thought experiment shows us, because we know n goes into infinity, it's the same as focusing on h going into infinity with this substitution. And now we simplify. And I notice inside my parentheses I've got an r on top and an r on bottom. They just cancel out. And so this leaves me with the limit as h approaches infinity of 1 plus 1 over h to the power of hr. But I notice that's really not a lot different than what I had here when I had nt. That r is now on the outside, and I can separate it out. And I can think about having it outside a set of brackets. And we already showed that it can go all the way outside the limit, so I can put the brackets right here and recognize now that internally my limit variable is h, and the only variable inside my limit now is h. And so I've been able to get rid of everybody. But I've got to remember that there was more to this here. Remember, I had a p and a t also as part of my formula. So if I substitute all of this back into here, what I now get is p times, in brackets now, the limit as h approaches infinity of 1 plus 1 over h to the power of h. And then outside this bracket, I had a t, and I now also have an r. And they can combine together, again, just using our rules of exponents, into an RT. And so what we have here is, this is my compound interest formula, but I'm taking n to infinity. Now I know there's no n showing here, but we did show here that with this appropriate substitution, it's no different than thinking about h approaching infinity. And so this is the exact same thing, and this is essentially the answer to the continuous compound interest formula. It's just not a helpful answer. So next, we explore what can we do to find, does this limit have a value, and if so, what is it? Okay, to explore our limit, we're actually going to define something new now called a sequence. Now, a sequence is actually pretty straightforward, so don't worry too much about more new things showing up here. Basically, a sequence is an ordered list. Now, we've already encountered lists before. We talked about the list of natural numbers, the list of prime numbers, but the specific thing about a sequence is that the order of those numbers actually matters. What comes first versus what comes second makes a difference. Switch any two terms, remove any terms, you've got a completely different sequence. So now some notation. Since it's a list, we use braces, and we give our sequence a variable name. I like to keep it simple. Let's just call it A. Then we have to index our sequence, so we know which item of the sequence we're talking about. So I'm going to use the variable h, and we write it as a subscript. Then we close the braces. And then we need to know the starting and the ending value of the sequence. So I'm going to start when my h equals 1, and I write it here. And I'm going to end at infinity, meaning I'm not going to end. This is an infinite sequence. Now, a sequence can be composed of anything, but if it's random, it's not very interesting mathematically. So instead, we prefer a sequence where we can actually generate each term based on some formula. And so, the formula I'm going to use to generate each term here shouldn't be too much of a surprise. It's 1 plus 1 over h to the h. And I also keep my same directions starting at h equals 1 and going to infinity. So I'm going to use this sequence to explore some ideas to see what happens. Now, what I'm going to explore first is I'm going to look at what happens, how any term in the sequence compares to the previous term. And we do that by using a ratio. And so I say, okay, I want to know what happens if I take a sub h plus 1 divided by a sub h. Okay? And all I do is substitute, do some algebra, see what happens. So hang in there with me, pause it if you need to, follow along if you'd like to. Leave me a comment if you're actually following along. I think that'd be pretty kind of cool. Alright, so a sub h plus 1 basically means for all of my h's here, I'm going to put in an h plus 1. So I've got, in my numerator, 1 plus 1 over h plus 1 to the power of h plus 1, all over, and now a sub h, well, that's just my formula. So I've got 1 plus 1 over h to the power of h. Now, in each of these sides, I've got a summation with fractions. I'd rather have them just be one fraction. So to do that, I need a common denominator. Well, here, my common denominator is going to be h plus 1. So I change 1 into h plus 1 over h plus 1. Because you take the same thing divided by itself, you get a 1. So all I'm doing is multiplying by 1, which means I change nothing. So the value doesn't change. So this becomes h plus 1 over h plus 1. And then my common denominator, so now it's h plus 1 plus 1. Oh, well, that's easy. That's just h plus 2 over my common denominator of h plus 1, still to the power of h plus 1, all over. Do the same thing here. Here my common denominator is going to be h, so I think about multiplying this by h over h, so that leaves me the common denominator of h, so I've got h plus 1, so I have h plus 1 in my numerator over h, all to the power of h. And now I've got a fraction divided by a fraction. Yuck, nobody likes that. So I'd rather take this fraction and move it into the numerator. To do that, we can think about doing its reciprocal. So I can really think about this as, instead of divided by this fraction, as multiplied by the reciprocal of this fraction. Remember, reciprocal means to flip. So this is no different than, I still have h plus 2 over h plus 1 to the power of h plus 1, now times the reciprocal here, h over h plus 1, all to the power of h. I'd like to make it a little nicer. The problem I'm running into now is my exponents don't match. Sure, we have a common denominator, but that's not going to help me if my exponents aren't the same. I can't combine them in any way at this point. So I say, well, what if I could? if I could turn this into an h plus 1, I would have to do that by multiplying by another one of these, another h over h plus 1. But if I did just that, I would change the value. So I can't just multiply by h over h plus 1, but if I multiply by that and its reciprocal, then I'm really multiplying by the value of 1, which means I'm not changing anything. So let's see what that looks like. So down here, I say, okay, I have h plus 2 over h plus 1 to the h plus 1 times h over h plus 1 to the h times h over h plus 1. I'm choosing to multiply by this so that I have the same things here. But in order for this to not change the value, I need to also multiply by its reciprocal, which is h plus 1 over h. And to see why that works, think about how h plus 1 and h plus 1 cancel out, h and h cancel out, so that would disappear, leaving me exactly what I had before. But I'm going to leave it in right now, but we now know the value hasn't changed. So now I combine again. All right? Well, these two things, this says I'm multiplying h of them and then one more, so this becomes h plus 1 in my exponent. So I still have what I'm starting with, h plus 2 over h plus 1 to the h plus 1, now times h over h plus 1 to the h plus 1, and then I've still got this extra factor that I needed to keep the value from changing, and that's over h. And then because these have the same exponent, I can multiply their bases. So I can multiply these two fractions together and combine them under the one exponent. So that's what I'll do next. All right, so now when we multiply just straight across the top, straight across the bottom. I've got h plus 2 times h. That h has to be distributed to each term. So what I've really got going on in the numerator now is h times h, which is h squared, plus 2 times h, which is 2h, all over. Now in the denominator, I've got two binomials, which we've done plenty of times. So I have to think distribute. First and the first, h times h, that's h squared, plus first and the last, h times 1, that's h, plus the second one here times the first one here, that's h, plus the second one here times the last one here, that's 1. This is all to the power of h plus 1. And then don't forget our little extra buddy there that we need to keep the value from being different, h plus 1 over h. Hang in there. There's a lot going on, I know. What we focus on next is combining like terms. So notice here that I've got an h and an h. So I've really got two h's. So I'm just going to save myself a little bit of space and just rewrite that here. This is really plus 2h. And now as I look at this, I'm thinking, all right, look at the top and look at the bottom. These are very, very similar. There's something missing. I'm missing a plus 1 in order for that to completely cancel out. Well, just as over here I said, if I could put something in, that'd be nice, but I have to put something else in to balance it out so the value doesn't change. I can do the same thing here. I would love to have a plus 1 here, but you can't just put a plus 1 in without changing its value. Well, how do you balance out plus 1? You balance it out with minus 1. And so that's what I'm going to do. So I'm going to think I can do this. I can add 1 as long as I also subtract 1. So all I've really done is add 0, so the value doesn't change. But now what I see is that I've got something that I like a lot more. I've got h squared plus 2h plus 1 minus 1 over h squared plus 2h plus 1. So I can split this into two fractions, where I put the h squared plus 2h plus 1 in the first fraction and the minus 1 in the second fraction, so that I get some canceling going on here. And so that's what I'm going to go ahead and do. Now because of that, I'm going to have this top and this bottom match, which means they cancel out into a 1. And then what I'm left with is plus, the other half was a negative 1 on top, and in the denominator, I've got h squared plus 2h plus 1, all to the power of h plus 1, and then don't forget my little buddy there, my extra, h plus 1 over h. who's just kind of hanging out. And you may look at this, and you may say, what the heck was the point of all of this? We started off with something that looked nice enough, and we ended up with this ugly hoobity-goobers. How in the world does that help me? Well, it turns out we've already seen exactly how it's going to help us. Do you remember at the beginning when we took a little detour and we studied this expression that we were like, why are we taking the time to do this? This is why. We said 1 plus c to the power of k is greater than 1 plus kc. So what I want to focus on is, do I have a 1 plus c to the power of k here? So I'm going to temporarily ignore my little buddy, and I'm just going to focus on this portion right here. And I've got 1 plus something, could be a c, to the power of something, which could be a k. Do they meet the requirements? Well, we said k has to be greater than or equal to 2. Here I have h plus 1. Well, h, we said, goes from 1 to infinity. So the smallest it could be is 1 plus 1, which is 2. So absolutely, my exponent meets the rules for k. So the last thing I need to know is, does this meet the rules for c? In other words, can I say that negative 1 over h squared plus 2h plus 1 is greater than negative 1? Let's find out. Okay, so I've separated out just this part right here. We've already said that our exponent works for k, because h plus 1, the smallest it can be, is 2, and k has to be greater than or equal to 2, so we know that works. And now we wanted to say, does this piece right here, which fits into c, does it work, meaning is it going to be greater than negative 1? Well, I have a negative 1 in the numerator, and I'm dividing by an expression. So let's consider what that expression could be. Remember, h is between 1 and infinity. It's a natural number, so it's always positive. So I've got a positive squared plus 2 times a positive plus a positive. And the smallest it could be is when h equals 1. Well, 1 squared is 1, 2 times 1 is 2, plus 1, that's 1 plus 2 plus 1, that's 4. So the absolute smallest my denominator could be would be 4. Now in division, it's kind of in reverse. The bigger the number I divide by, the actual smaller that I get. And so here I'm thinking in terms of magnitude again, absolute value. And so ignoring that negative for right now, I've got 1 divided by 4 is the biggest magnitude that I can make this. Which means as I increase h, my denominator is going to get bigger and bigger, which means this value, this magnitude, is going to get smaller and smaller, closer to 0. And then I put my negative back in, so I know it's negative, but it's smaller than 1. The farthest away from 0 I get is negative 1/4. And after that, I just get closer and closer as I increase h. So therefore, this is between negative 1 and 0, which means it's greater than negative 1. And thus, this does meet the criteria for c. So this meets the criteria for c, this meets the criteria for k, thus, which we had proved by induction, says I can now make this claim that this must be greater than 1 plus kc. K being h plus 1 times c being this one right here, negative 1 over h squared plus 2h plus 1. So now I know that this is true because of what we had proved earlier and because this meets that criteria. So now I'm no longer concerned with this hoobity-goobers, and I'm going to be more concerned with these hoobity-goobers. All right, so now we did leave out a piece from before, the h over h plus 1. We're going to continue to leave it out for now. We're just going to work with this bad boy first. We're going to see what happens here, then we'll come back to it. So don't forget that it's there, but for now, just for space purposes, we're going to leave that out. Okay, so this is multiplying by this, which means it's really a fraction. You can think of this as a fraction over 1. And when I multiply my fractions again, I multiply straight across the top, straight across the bottom. So this really gets me, now this is negative, so I got to carry that negative through here. This is going to be 1 plus negative h minus 1 over h squared plus 2h plus 1. And then I want, again, to make this into one fraction. So I think about my common denominator. And I say, okay, well, my common denominator here is h squared plus 2h plus 1. And so I multiply that on both the top and bottom here, so I'm multiplying by 1 and not changing the value. And then I think about what happens as I combine them. All right, so that means I have an h squared plus 2h plus 1, and then minus h minus 1. So I'm taking away an h, and I'm taking away a 1. So what that really leads me to is I have h squared plus h, because I took 1 away, and that's it in my numerator, because I no longer have that 1 there. And then I still have this over the denominator, h squared plus 2h plus 1. Now, the next thing I recognize is that both of these terms have an h in them, so I can factor that out. And then I write the leftovers. I've got an h left over here, and I've got a 1 left over here. Now, this denominator is a little trickier, and unless you really pay good attention in algebra, you might not readily see what we can do with this. But the trick is to recognize where this came from. We created this by multiplying h plus 1 times itself. It was h plus 1 times h plus 1. So I can actually rewrite it as that. I can undo that expansion that I did and have it like this, h plus 1 times h plus 1. Now, look what we've got going here. We've got an h plus 1 and an h plus 1 in both the numerator and the denominator. So these cancel out, and this now leaves me with h over h plus 1. But remember, that's just from this part right here. We took this from an expression that had a little extra guy hanging around. And we know that I could re-multiply it on the up here, and because it's a positive value, it doesn't change this inequality, so I could re-multiply it down here. So then what this will now lead to, and here I don't just use an equals because it's not equal, I'm going back to what it leads to, is I still have this h over h plus 1 multiplied by that leftover that I had before, which was just h plus 1 over h. Ooh, now that looks really nice, because what do I got? I got an h on top, h on bottom. I got an h plus 1 on top, h plus 1 on bottom. If you cancel everything out, you are left with 1. Now we put this all together. How did we start all of this messy algebra? We started it by saying, I want to look at the ratio of a sub h plus 1 over a sub h. And in that process, we had equal sign, equal sign, equal sign up until here, where we get a is greater than sign, and then equal sign, equal sign, equal sign, all the way to here, where we get a 1. So all of that messy work was to show this relationship right here. A sub h plus 1 over a sub h is greater than 1. Now multiply both sides by a sub h. All right? So that I'm left with a sub h plus 1 on the left is greater than a sub h on the right. What does that tell us? Remember, this is my variable from my sequence. And it says that as I go from one term to the next term, I am always bigger. Always bigger. This is a strictly increasing sequence. So as I find values, as I substitute in 1, 2, 3, and 4, and so on for h, each time I do that, I'm always going to get a bigger and bigger value. So I could kind of write out my sequence like this. I could say the terms in my sequence like this. A sub 1 has to be less than a sub 2, has to be less than a sub 3, has to be less than dot, 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 is less than whatever a sub h I come up with next is less than dot, 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 because it goes into infinity. And so all of that messy algebra was to show me that looking at this and thinking of it as a sequence, each term in the sequence can be written in a strictly increasing order. Now that's nice in and of itself, but it still doesn't help me know what happens at infinity. So to do that, we're actually going to explore a different but very similar sequence. Okay, now for the new sequence. Because it is a new one, I'm going to give it a new name. So in this case, instead of A, I'm just going to call it B. And it's the same index, h. H still goes from 1 to infinity. And this was our original formula for A. I'm going to modify it very slightly. For B, I'm going to change the exponent to h plus 1. So as you can see, a very similar sequence, but still different. And now I'm going to explore a ratio again, but I'm going to do it in reverse. In other words, I'm going to say, how does one term compare to the next term instead of to the previous term? So we write that one, essentially, as the reciprocal of what we wrote before. I want to explore this ratio right here, b sub h over b sub h plus 1. And we're going to essentially follow all the same algebra. So I'm going to try to be a little quicker with this one because we're doing basically the same thing. The numbers are going to look a little different because the sequence is slightly different, but the ideas are all the same. So substitute in b sub h. Well, that is just 1 plus 1 over h to the power of h plus 1 all over b sub h plus 1. So I put in an h plus 1 for every h. So this is 1 plus 1 over h plus 1 to the power of, careful, it's h plus 1 plus 1. So that is h plus 2. I want these sums to be combined into single fractions. So common denominator of h, that means this is h over h. So in my numerator, I have h plus 1 over my common denominator h, still to the power of h plus 1. And in my denominator, I have common denominator of h plus 1. And so I think h plus 1 over h plus 1. So I've got h plus 1 plus 1 in the numerator. This is h plus 2 over h plus 1, all to the power of h plus 2. Again, fraction divided by a fraction, not so nice. So instead of divide by this fraction, I can multiply by its reciprocal. So my first one stays the same. I've got h plus 1 over h to the h plus 1 times, now flip this fraction, h plus 1 over h plus 2 to the h plus 2. And again, I want to combine them. To do that, I need to have the same exponent. This one's smaller, so I'm thinking, okay, I need to multiply by another one of these in order to increase that exponent by 1, but that would change its value. So to balance that out, I also multiply by the reciprocal of that so that they all cancel out. So the first thing I do down here is I'm going to multiply by another one of these. So I've got h plus 1 over h times h plus 1 over h to the h plus 1 times h plus 1 over h plus 2 to the h plus 2, now times the reciprocal of this new guy that I had in here, which is h over h plus 1. And that way they cancel out. As you can see, they cancel out, so this is like multiplying by 1. I combine these so that we can see I've got h plus 1 of these, and I need one more, so they become h plus 2 of them. So I've got h plus 1 over h to the h plus 2 times h plus 1 over h plus 2 to the h plus 2 times h over h plus 1, that little leftover guy. And now I simplify. Same exponent means I can multiply the bases together. And again, I want to be careful. I've got this times itself. There's a binomial, so I'm distributing. I've got h times h, that's h squared. I've got h times 1 plus h. I've got 1 times h plus h. And I've got 1 times 1 plus 1, all over. Similarly, in the denominator, I have to distribute h times h and h times 2. So I've got h times h is h squared plus 2h. And then this whole thing is still being multiplied by those extras, h over h plus 1. And again, to save space, I'm going to simplify. I've got plus h and plus h. That's really plus 2h's here. And then again, just like last time, oops, I almost forgot my exponent. Good call, whoever saw that. So now I say these are very, very similar, but not quite perfect. But it turns out that's okay, because as long as it matches the denominator, that's all we really care about. So I see right here I've got h squared plus 2h in both the numerator and the denominator, separated by a 1 here. So I can already split those into two fractions. So on the left, I'll have h squared plus 2h over h squared plus 2h. That's just a 1. And then on the right, I have a 1 over h squared plus 2h. And then still times, to the power of h plus 2. And then still times h over h plus 1. And just as the same thing we did last time, we look at just this portion right here. And we recognize how it fits our, well, we check to see first, does it fit the criteria we had, 1 plus c to the k? Can we still use this? Starting first with k is my exponent, k has to be greater than or equal to 2. The smallest h can be is 1, 1 plus 2 is 3, 3 is definitely greater than or equal to 2, and then it only grows from there. So that's valid for k. Is that valid for c? Again, we'll find out. Okay, just as last time, I'm going to separate out just this part right here, remembering there is a leftover guy, but we're not going to worry about him right now. And then I say, okay, we've already said that if I'm thinking of this as 1 plus c to the k, I already said this works for k. Here's the value for that could be c that I'm concerned with. It has to be greater than negative 1. Does it meet that criteria? Well, again, h can only be positive based on our restrictions. Positive squared has to be positive, plus positive times a positive, all has to be positive. 1 divided by a positive, 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 positive. C is definitely positive. This is definitely qualifies for C. So this will meet that same criteria. So we can say, without doubt, that this is greater than 1 plus kc. K being h plus 2 times c being 1 over h squared plus 2h. And now we just simplify. Okay. Well, again, I'm multiplying here. This is really like a fraction over 1. So I multiply across the top, across the bottom. This is just 1 plus h plus 2 over h squared plus 2h. And again, I'm adding here. I'd rather make them one fraction. So I look at common denominator. Well, that's going to be h squared plus 2h. So I think multiply this by h squared plus 2h over h squared plus 2h, so its value doesn't change. So in the numerator here, I've got h squared plus 2h plus h plus 2. All right, well, what does that look like here? Well, that gives me h squared plus, I said plus 2h plus h. Well, that's plus 3h plus 2 all over h squared plus 2h. Well, that's not nearly as nice as we had before. So where do we go from here? Now, this part's a little trickier, and it does require you to remember a little bit of your algebra. But we can kind of figure this out by guessing what we need to do and then verifying that it does in fact work. So let's start with the denominator. We've already seen something like this before, and it's easy to factor. I've got an h in both spots here, so I know that in my denominator, I can factor out that h and write the leftovers as h plus 2. I can also think about that extra guy that I saw before. Now remember, when we took this out from our previous part, there was a little guy hanging out at the end. And that guy hanging out at the end was h over h plus 1. Math is beautiful, and math forms patterns, and math has repetitions. So I have a gut feeling that I ultimately want what I have left here to be the reciprocal of this, to be h plus 1 over h. Well, I've got the h here, which means I need the h plus 1 in the top, but then it would have to cancel out with this h plus 2, which means I need an h plus 2 in the top as well. So what does that look like? Well, let's write that out. In the numerator, I'm saying I should have something that looks like this. H plus 1 times h plus 2. Let's expand it out and see what that looks like. All right. Well, what's h plus h? Or sorry, h times h, that's h squared. Then h times 2, that's 2h. 1 times h, that's h. 1 times 2, that's 2. Combine like terms here in the middle, 2h plus h. Well, that's just 3h. Wait a minute. H squared plus 3h plus 2. That's exactly what I have, which means this factors exactly into this. So just by saying, I wish that this were true, I could then do some math to demonstrate it must be true. So even if you don't remember your algebra, you could still use a little bit of gut and intuition to ultimately get this figured out. So I know this is the same as this, so I write it here. H plus 1 times H plus 2. And then I recognize that the H plus 2 and the H plus 2 cancel out, which leaves me with H plus 1 over H. But then I remember there's more to this problem. This was pulled away from something else, so I need to reintroduce that something else back into this. And so it's what I just left off with, H plus 1 over H times, this was the something else, H over H plus 1. Now what happens? H and H plus 1, all cancels out, leaving me with 1. And so, just like last time, we say, where did we start? This whole thing started with B sub H over B sub H plus 1. We had equals, 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 and then we had is greater than, equals, 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 all the way to 1. And then we multiply both sides by B sub H plus 1. And we get B sub H is greater than B sub H plus 1. Meaning, if I think about my sequence in reverse, then my previous term is always greater than the next term. So whatever term I pick, the one before has to always be greater. We could even flip this around and write it like this. B sub H plus 1 is less than B sub H. So as I increase terms in this sequence, I'm always getting smaller, strictly decreasing, always getting smaller. So I can also write this like I wrote my A's, but I'm going to write it in reverse here. So if B sub H is always bigger than B sub H plus 1, that means my first one, B sub 1, has to be the greatest. And we like to think left to right is smallest to largest. So I start on the right here, and I say that has to be greater than B sub 2, which has to be greater than B sub 3, which has to be greater than dot 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 B sub n, has to be greater than dot dot dot. So again, it's an infinite sequence. That's how we defined it. But we know it's strictly decreasing, so I can write the terms like this and say that they are separated like that. So similar to how we did A, but a little bit different, kind of reversed basically. It's one more thing we need, then we can see how we can put this all together. Now, start with A sub H and recognize that this is our formula. It equals 1 plus 1 over H to the H. Now, what I'm actually going to want to do is I'm going to want to increase this. So I'm going to actually put this inequality symbol right here and say this is less than what I'm about to do next. And what I'm about to do next is to take what I just started with, 1 over 1 plus H to the H, and multiply by 1 plus 1 over H. Now this has to be positive, because H has to be positive. And so this is definitely an increase, because it's a number plus 1, so it's bigger than 1. I'm multiplying by a bigger number than 1, so I have to be increasing, so this inequality is valid. Well, look at this. I have the same things being multiplied. Here's H of them, and here's one more. So this is just equal to 1 plus 1 over H to the H plus 1. But that's just equal to B sub H. So what I've shown here is, again, I've got A sub H, an equal sign, then an is less than sign, then an equals equals, B sub n. Putting this all together tells me that A sub H is strictly less than B sub H. Well, what does that mean? Pick any value for H, plug it into both of the sequences we created, the A and the B, and you're going to find that A will always be smaller than B, no matter the value of H. We put no restrictions on H here. And therefore, A is always smaller than B means I can combine the way we wrote those two things out. So we had, remember, A sub 1 is less than A sub 2 is less than dot 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 is less than A sub n. But A sub n, H, I'm sorry, my H's look like n's. But A sub H has to be less than B sub H. Has to be. So less than dot dot dot, because H can continue to grow, has to be less than B sub H, which we know is less than b sub 2 is less than b sub 1. So we can combine those two together because think about it, if I put in a 1 for a, it has to be less than b sub 1, and a 2 for a has to be less than b sub 2, and a million for a has to be less than a million b sub a million, and a million and a trillion and a quadrillion and all this kind of stuff has to be. They have to be less than each other. So what does that show us? Use your intuition. We started all of this by talking about a limit. As h approaches infinity, I care about this right here. Well, that's just a. So now I can focus on just the a. As a goes into infinity, it's constantly less than some value here. Constantly. It will always be less than some value here. And to kind of make it more concrete, let's actually put some limiting values here. All right, so a sub 1. Well, let's just plug it in. What's 1 plus 1 over 1? Well, 1 over 1 is 1. 1 plus 1 is 2. To the power of 1. 2 to the power of 1 is 2. So I can replace this with a 2. And let's go to b sub 1. Okay, we'll plug in a 1 here. 1 plus 1 over 1. 1 over 1 is 1. 1 plus 1 is 2. And then 1 plus 1 is 2. 2 to the 2 is 4. So this is 4. So here I have that the limit of a sub h is somewhere in here, and that somewhere in here is between 2 and 4. In other words, my limit approaches a specific finite value. So not only does the limit exist, but it has a value to it. That's what we wanted to see. So all of that work that we did, changing to sequences, all that crazy algebra, and that weird abstraction we did at the very beginning, all of that goes to show me that in fact this limit does exist, and it's a finite number. Now how do we use it? All right, so here is the limit we were exploring. Here is the continuous compound interest formula we found that contains that limit, and we just showed that this limit exists and is a finite number. But we don't know the value of that number, though we do know it's between 2 and 4. So let's just give it a name and say that name represents that value. And so what we do is we actually define it. We call it a lowercase e. And we say e is equal to this limit. And e actually comes from the first letter of the last name of Leonhard Euler, a man we've actually already studied one of his formulas previously because of his extensive study of this number. And so we name it in honor of him, so it's sometimes referred to as Euler's number. We'll just call it e for short. And so since that's what this limit is, we can come over here and we can substitute that in, and that means we have a equals p times e to the power of RT. And that, my friends, is the continuous compound interest formula. All we need to know is the value of e, because remember, we know p, r, and t at any time. We just figure out the value for e, and what this basically says is this is the maximum amount of interest that can be earned. No matter how many compounding periods you want to have, you can't exceed this, because we showed that e exists. And I think that's kind of nice. Both mathematically, it's beautiful, but also for practical purposes, you wouldn't want some scumbag out there to be able to take as much money from you as they want, meaning an infinite amount of money. So it's kind of nice to think about this. You could find the meanest loan shark out there who can charge you a ridiculous amount of interest. And no matter how much he tries to compound that, there's still going to be a finite limit. Now don't get me wrong, that limit may be something you can't afford or could ever afford, but it's still a limit. It's not infinity, and that's pretty awesome. Now what's also kind of cool is we can kind of explore what E really means in more of a practical sense as well. So just focusing on E again, that's this limit. Let's just take a look at just this part right here. So this is just 1 plus 1 over h to the power of h. And I'm actually going to return it back to n, okay? Because h is just a dummy variable, so it doesn't really matter what letter I have here. So I'm going to go ahead and make that an n again. And I'm going to say, think about the compound interest formula. Okay? And if you remember that one is a equals p times 1 plus r over n to the nt. And I want to compare that to this and say, okay, well, what would p be in this case? P would be the number I'm multiplying by right here. That's just a 1 if nothing's written there. So I'm saying P equals $1. Then I look in here and say, what's R? R is right here. Well, that's a 1. Now be careful, it's a percent. So this really means 100%. So R equals 100% per year. And then I've got T out here, so it's N times T. Well, what is N being multiplied by? Well, 1. If nothing's there, it's a 1. So I have T equals 1 year. And so what we can also think about this value for E is again, it's still as N approaches infinity, but it's the idea that take $1 and charge 100% interest and compound it continuously for 1 year. How much money do you have at the end of that year? That is the value for E. So that kind of gives us one way to compute it. Now, computing E turns out to be a lot harder than you might think, and I'm going to do a follow-up video where we'll talk about that. But in the meantime, we showed that there is a formula for continuous compounding interest, and this value for E is a finite value that actually exists. So remember, you watched it, you can't unwatch it.
It's obvious I'm wide and nerdy. Think I'm just too wide and nerdy. Think I'm just too wide and nerdy. I'm just too wide and nerdy. Look at me, I'm white and nerdy.